Okay. Well, we are talking about uh, ordinary differential equations, ODEs, using separation of variables. Um, and there's one last thing that I want to bring up. So remember that an ordinary differential equation means that there's only one independent variable. Okay. But you can have more than one dependent variable. Um, and actually, that's going to be an important thing for us. The most the example that we're going to see the most is like you could have something that's like x prime is equal to um, 50, y prime is equal to negative 2t, something like that. Okay. And you could write this as in a vector form. Okay, well, that's an example of one independent variable, t, and two dependent variables, x and y. Okay, we're going to do that stuff all the time. That's just doing kinematics in vector form. But there's one thing that you need to keep in mind. When you have more than one dependent variable, you have to think about whether it's a coupled system or an uncoupled system. So we can use separation of variables in the case of uncoupled. So we can do these. If it's coupled, we can't do them. There are ways to deal with it that you'll talk about in Calc 4, but we're just not going to talk about it. So we can't do these. Yes, great question. And so an uncoupled system of ordinary differential equations is when the dependent variables stay in their own equations. And I'll give you an example of a coupled one. So for example, x dot is equal to 2xt, y dot is equal to y squared, t squared. That is uncoupled because there's one equation that has all the x's, one equation that has all the y's. Okay, so this is uncoupled, and this we can do. What we can't do is x dot is equal to 2xy t, y dot is equal to x squared t squared. that's coupled. And you need other techniques to do those.
So you wouldn't solve them using dynamic?
You wouldn't. So for an uncoupled case, we would do that using separation of variables in this class. For a coupled one, there are ways to approach it, but we're not going to talk about them. So in this class, that's just, I think the only way you'll see these is in questions where I say, can you do this or not, basically, you know? And no, in this class, you can't. And like I said, the types of differential equations that I'm going to have you solve in this class, I really think in almost every case, they're the only differential equations that you'll ever be expected to do in a mechanics class without further instructions. Okay? If they expect you to do harder anything, they'll remind you how to do it. Okay? But this one you'll tend to be held kind of like it's sort of the simplest case, and people want you to recognize how to do that stuff in the future. Okay, well, this can be written in like a matrix form, so I want to show you what that looks like. And so first, I just have to tell you how to do a simple matrix multiplication. So if you have the matrix A, B, C, D, and you're multiplying it by the vector EF, you're going to get a vector as output, and the first element of the vector you get as output is going to be the dot product of this and this. So your first component of the vector will be AE plus BF. And then the second component of your output vector is going to be a dot product between this row and this column. So you're always taking dot products of a row on the left with a column on the right. And so this one is CE plus DF. Okay, so a system of ordinary differential equations can be written as like, let's call it A, B, C, D times xy, a vector of your dependent variables, is equal to x dot y dot. Okay. And so is this coupled or uncoupled? Well, it depends what A, B, C, and D are. Like notice this is equivalent to, you can think of this as x dot is equal to ax plus by, and y dot is equal to cx plus dy. Okay. So we can only solve this if B and C are equal to 0. Okay, otherwise it's a coupled system. Okay, there's like one homework question I think you have to do like this. Maybe there's two of them, but where you just have to make sense out of the matrix form of it, Okay, any questions about coupled and uncoupled? So we're only dealing with ordinary differential equations, and you should get used to recognizing what's ordinary and what's partial. We're only using separation of variables, so you should get used to identifying when you can use separation of variables and when you can't. And we're only doing uncoupled systems of differential equations, so you should, get used to recognizing uncoupled and coupled. Okay. And that is all of the math preliminaries. So now we're going on to some dynamics. So the first dynamics topic is really the topic that you spent almost all of Physics 1 on. And that is particle kinematics. In a non-rotating coordinate system. Okay, so let's remind ourselves what all this stuff means. So what's a particle?
The smallest unit of it's a point, but 3 dimensions.
Okay, that's right. There is a distinction to make. It's not necessarily a very small thing. We'll treat big things as if they're particles, but it's like a mathematical treatment where we act like the object only exists at a point at its center of mass. Okay, so when you do planetary physics and stuff, you treat planets as particles. They're not small, but it just means that you're treating their location as if it only exists at their center of mass. Okay, so it's a mathematical treatment of an object. As having no length dimensions. Bless you. So it has no size. Does it have mass? Yes, exactly. But it does have mass. Its location is the center of mass. And because it has no length dimensions, there's no way to differentiate between one side and another side. And that means that you can't do any treatment of changes in orientation. You can't tell whether it's upside down or right side up or facing this way or facing that way. So there's no change in orientation. Let's say there's no way to address changes in orientation. And we'll see that when we get to kinetics, bless you, what that means is there won't be any use for moments when we're talking about particles. Okay, only forces, only Newton's second law. And what about kinematics? They could not have made that more confusing with kinematics and kinetics. That's unnecessarily confusing. But kinematics is the simpler one, where you're not talking about the causes. You're only talking about relationships between time, position vector, velocity vector, and acceleration vector. No causes of the motion. And so the causes I'd be talking about would be like mass, force, energy. Okay. Another way to think of kinematics is it's all stuff that if you were investigating the motion of an object in a room that was all carefully gridded out on the walls and the floors and everything, and you had a video camera in the corner, you could do kinematics just based on what that video camera is showing you. You can't do kinetics that way. Okay. So this is like the simpler case, the longer word in the simpler case. Kinetics is the more complicated and the shorter word.
Kinetics related to kinetic energy?
Yeah, yes. I don't remember what the. Yes, it's related, but it's not a very helpful relationship, I guess, in understanding what's going on. Okay, this topic is divided into 4 sections. So the first one is just that the acceleration is the time derivative of the velocity, and it's the second time derivative of the position. Then the second one is using the chain rule. And we'll do this when we know the velocity vector as a function of a position variable rather than time. And then the third and fourth are kind of connected. The third one is the relative motion equations. And the fourth one is circular and spherical motion. These two go together naturally. So these are used together. This is going to be the biggest use of these things in this class in rigid body motion. Okay, so circular and spherical motion. There's since this is the first time I'm bringing these two things up, I want to give you a first crack at like a distinction between. I just said that particles don't have any orientation changes, and orientation changes and circular and spherical motion are connected in a lot of ways, but they're different. So this is a change in orientation. Okay. This is a spherical or circular motion. See what I'm talking about? You can put them together. But mathematically they're different. And so you need to know which one you're thinking about, you know. With particles, we never do this. I mean, maybe it does that. We just don't have any way of knowing. We don't have any way of calculating it. Particles only do their location changes, and that location change can be in a circle or a sphere. Okay, so the first one of these categories is the acceleration, we can think of these as definitions. So the acceleration is defined as the time derivative of the velocity, and it's defined as the second time derivative of the position. These always hold. In fact, these even hold in the case of rotating coordinate systems. It's just that calculating those derivatives gets more complicated. And so if you only hear one thing in this class today, maybe in this whole class, this whole semester, okay, the one thing that I want you to be so clear on is, so remember, okay, now, if you only remember this one thing from this whole semester, you're not going to do super, super well in the class, okay? But still, this is the best thing to remember. Don't think of it this way. Don't think that the acceleration is the derivative of the velocity, which is the second derivative of the position. Okay, that derivative relationship has to be with respect to time. So no, these derivatives have to be with respect to time. So in using these derivative relationships, there's two directions you can go.
So what would we write instead of the A?
Well, just it's not the prime relationship. It's so that prime just means take the derivative with whatever you have, you know. So if you have an x, take a derivative with respect to x. If you have whatever, the real relationship is this. It has to be derivatives with respect to time. Okay.
But it's not like a partial derivative.
Right. It's a total derivative. That's right. And so if you have other variables, you have to account for that using the chain rule and stuff like that. But we won't have that problem in this class. If you get into anybody who takes like higher level continuum mechanics later on, if anyone just ends up going in sort of a mathier direction, then you'll have to deal with this kind of stuff. But okay, so there's two directions you can go. If you're given the position vector and you want to go then to the velocity vector and maybe then to the acceleration vector, this is the easier of the two. Because you don't need boundary conditions. You're just taking derivatives. So you can think of this as the derivative direction. But the other direction that you can go is, say, you start with acceleration and then you want to go to the velocity and then maybe you want to go to the position. This way is a little more involved. This is using separation of variables. And you need boundary conditions. This is the integral direction. So if you're given position as a function of time, then you're pretty much set. Everything's pretty simple. If you're given velocity or acceleration as a function of time, then you're likely going to have to use boundary conditions for whatever you're trying to find. Okay. Okay, let's do a couple examples. We've done examples like this as part of the mathematical preliminaries. So for the first one, let's say that the position vector as a function of time is equal to t squared. And we want to know what are the velocity vector as a function of time and the acceleration vector as a function of time. Well, which direction is this? The derivative direction or the integral direction? Yeah, we're just taking derivatives. So the velocity is just the time derivative of the position. So that's 1, 2t. And the acceleration is the time derivative of the velocity, or the second time derivative of the position. So that's 0, 2. And it's always a good idea to think about units. So let's say that this is in, say that this will give you values in SI units. So for the position, that would be meters. Then this velocity would give you units of meters per second. And this acceleration would give you units of meters per second squared. So those are the SI units.
So the dot, so like for that one, the velocity vector equals that's the position, the
Yeah.
derivative of the position vector.
With respect to time is what the dot means. Yep. Dot always means time.
Ah, okay.
Okay.
Always means that.
Yes, that's right. Otherwise, prime. Otherwise, you use prime for other stuff.
Okay.
But dot, time has its own thing because it's sacred, because time is so important in physics. Yep.
So then in this case, we could technically use a prime because it's only t?
It would be mathematically correct, but I'll take off every single point.
I see.
What if we wrote d prime of t?
Every point.
Yeah.
Yeah. Okay, so now for this one, we have velocity as a function of time is equal to t squared cosine t. And say again that this is in SI units. And let's say that we want to calculate the position as a function of time and the acceleration as a function of time, given that the position at time 0 is equal to 0, 50. And that's in meters. Okay, so are we going, for this one, are we going in the derivative direction or the integral direction? That's a trick.
Both?
Both, yeah, one of each. Okay, so the easy way is to get the acceleration. So the acceleration is the time derivative of the velocity. And so that is 2t negative sine t. And this would be in units of meters per second squared, once you got a value out of that. And now the second way, so I'm going to break this up into, we have that p dot is equal to t squared cosine of t. And I'll rewrite that as x dot is equal to t squared where x at time 0 is equal to 0 and y dot is equal to cosine of t where y at time 0 is equal to 50. Okay. Anybody want to take a second to look at this and make sure you see where everything's coming from? I'm just sort of rewriting things. Yes.
I have a general question. You meant to put like acceleration vector of t, like in parentheses t, or is that just like?
Yes.
That is meant to have t or no?
It is. That is right. These are both. Yeah. Right. Mm-hmm.
Could you scroll up a little bit?
Yeah. Okay, so now I'm gonna do this in two parts. So we have dx dt is equal to t squared. So dx is equal to t squared dt. I'm just using separation of variables now. Integrate both sides and you get x of t is equal to t cubed over 3 plus some constant of integration. And now the boundary condition says that if I plug in 0 for t, I get 0 for x. So set x equal to 0, set t equal to 0. And so this c comes out to be 0. And so update our function. And you get that x of t is equal to t cubed over 3 plus c, which is now 0. So this is it. And now we'll do the second one. We have y dot or dy dt is equal to cosine of t. So dy is equal to cosine of t dt. Integrate both sides. You get y of t is equal to sine of t plus a new constant of integration.
Is that negative sign?
No, we're integrating. Yeah, I always have to think about that too. And so now we'll use the boundary condition. We have that when time is equal to 0, y is equal to 50. So set y equal to 50. Set time equal to 0. sine of 0 is 0. And so C is equal to 50. And so now update. And you get that y as a function of time is equal to sine of t plus 50. And then if you wanted to put these together into the vector form, so position as a function of time is equal to t cubed over 3 for the x component, and sine of t plus 50 for the y component.
For the boundary conditions, when you're doing the numerical stuff, did you just make those up or?
Those I gave them in the, those were, so we're given that at time equals 0, the vector is 0, 50.
Oh,
Any other questions about that problem? Okay, so that's about all there is with that. We've done problems like that already. You don't have to, I mean, I'm trying to be really explicit here with the steps just so that, you know, you can understand clearly where you're at, but you don't have to write out every single one of these steps as long as I can follow what your thought process is. Okay, so now that's basically all there is to this time derivative relationship. But now we're going on to the second topic here, which is the chain rule. And this is going to come up pretty often. And you're going to need to use this when you're given the velocity vector as a function of a position variable. So the stuff that we just did, you're given velocity as a function of time. Now we're talking about using x or y or z or something. And you want to calculate the acceleration as a function of that position variable. Okay, so for example, let's say that you're given the velocity as a function of x is equal to x 10x. And you want to calculate the acceleration vector as a function of x. Okay, so the approach is I'm going to give this arbitrary variable lowercase s, and we'll let that be the position variable that we're using. And so say that we're given the velocity as a function of this position variable x. It could be x or y or z. Then the acceleration, the definition of the acceleration is the time derivative of the velocity, but we don't know the velocity as a function of time. Okay? So what we're going to do is, this is the chain rule step. We're going to write this as dv ds times ds dt. And this is a component of the velocity vector, which we already have. Okay, so let me start with the example that I just gave when we started this section. So let's say that the velocity as a function of x is equal to x 10x. And we want to calculate the acceleration as a function of x. Okay, and it's a very common mistake for people to make, to just think. So this is why I'm trying to emphasize all this stuff with the, where was this? Like, don't just think of these as derivatives. They're very specifically derivatives with respect to time, okay? So the mistake that, the most common mistake that people will make here is say, oh, this is easy. Acceleration is just the derivative of the velocity. And the variable I have is x, so I'm going to take my derivatives with respect to x. But that'll give you the wrong answer because it's the derivative with respect to time. So we have to use the chain rule here. So the acceleration is dv dx times dx dt. dv dx is 1, 10. dx dt is the x component of the velocity. So look up at the velocity vector. The x component is x. And so you get x 10x. Let me do another one just to solidify this idea. So let's say that we have the velocity of a particle as a function of z. And this vector is 5z, negative z, cosine of z. And we want to calculate the acceleration as a function of z. Well, again, the acceleration is dv dz times dz dt. dz dt is the z component of the velocity. dv dz is 5, negative 1, negative sine of z. The z component of the velocity is cosine of z. And so the acceleration vector is 5 times the cosine of z, negative cosine of z, negative sine of z times cosine of z. Yep.
For the first one, I'm just kind of caught up on how velocity is the same thing as accelerator.
Yeah, it's
Is that just random?
it's random. That's just the numbers it's just it worked out that way. It's totally random. Yes. It's not usually the case. So maybe I should come up with a better example there, but
It will be doing the same, but with the y component, we will use 10x instead of the just x, right? On the first example.
on this exactly. You would use the 10x in this example, and if it was a function of y in this one, you'd use the negative y or whatever in this case. That's right. Yep. Any other questions about this chain rule? Okay. We're going to make this one step more complicated. This is kind of what you would like to see. The only trick, as if you see it in this form, is recognizing that your variable, your independent variable, is not t, so you have to use the chain rule. Okay. But sometimes, instead of being given the velocity as a function of s, you'll be given the object's path as a function, and its speed as a function of a position variable. This is enough information to find the velocity as a function of s. And then it's just a chain rule problem. Okay, so the trick, the only thing that's different about these problems than the other ones is going from the path and the speed to the velocity vector as a function of that position variable. Okay, so here's the approach we're gonna take. So say this is the path that the object is on. Okay. And let's say that the object is moving from the right to the left. Okay. Now, notice that the velocity vector is always tangent to that path. So the velocity vector is tangent to that path, and it's equal to the speed times a unit vector tangent to the path. Okay? And we know in these kind of problems, We have a way to calculate the speed. So now we just need to use this path to figure out the unit vector tangent to the path. Okay. So to find this unit vector u, first we're going to parameterize the function. So for example, if the path is given as y is equal to x squared, well, a parameterization of this is that the vector, the position vector xy is equal to x squared. So that's our parameterization. Everyone with me on that? And then second, the derivative of the parameterization with respect to the parameter. In this case, our parameter is x. Is a non-unit vector, but it is a vector. Non-unit. Tangent to the path in the direction of increasing parameter value. So if it's going if this object is going in the direction of decreasing parameter, you have to multiply by -1. You have to multiply this whole vector by -1. Now that you have a vector that's in the direction you want, all you have to do is normalize it, find a unit vector in that same direction. Okay, so that's very wordy. You can go back and try to understand, think your way through that later on. But really, I think the way to learn this is just an example or two. Okay, here's the example. So let's say do I have one? So let's say that the path, or let's say that the object moves from from right to left along the path y equals cosine of x. And let's say that the speed of the object is 5x squared. So first, well, let's just do the step of calculating the velocity vector of the object as a function of x. Okay. Once we've gotten to this point, in order to calculate the acceleration, you would just use the chain rule like we did before. Okay. Okay, well, let's draw it out, see what this looks like. So there's the function cosine of x, and this object is moving this way. The parameterization is, it's always just going to be xy. And our y is cosine of x. So this just comes out to be x cosine of x. So there's our parameterization.
Can you explain that again?
Yeah. Well,
Like how
any vector is just going to, like, you can write it in this function form, like y equals cosine x, but the position vector is always just x for the x component and y for the y component. So all I'm doing is replacing the y component with that functional value. Okay. And let me just draw an arbitrary point. We're trying to come up with a unit vector pointing in this direction. So the first step is we know that if we take the derivative of this parameterization with respect to x, we'll get a vector that's tangent to the path. Okay, so we're just going to go d dx of x cosine x, and that gives us 1 negative sine x. Okay. This is tangent to the path at every x value. But there's one concern here, and that is that increasing x means going this way. Since this is going from right to left, we need the opposite direction, right? This would be giving us a vector going this direction. We don't want that. That's the opposite of the direction that we want.
How did you know that?
That it's going right to left, I gave that. The object moves from right to left. Okay, so it'll always say which way, because notice that the function, the path that it's on, doesn't say anything about which way it's going along that path, and so something has to tell you that.
We're assuming, unless told otherwise, assume standard coordinates, x, y coordinate system of x going increasing to the left.
I guess really that is not an assumption you have to make. I mean, you might as well to visualize it, I guess.
You also say, well, just for the ease of math, I'm having x start here and go this way and get bigger this way.
So like,
Physically
Yes, you could. So you could say like, yeah, like you walked around to the other side of it and watched it go. I guess you could do that, but don't do that. Okay.
So we'll always take that, moving from left to right will be increasing X.
Yes, that's right. Okay. Yes, that is it. That's a really good question, and you're right that that's something to think about. But yeah, let's always assume X is increasing from left to right, and Y is increasing from bottom to top. Okay, so we have a thing that's tangent to the path for any X, but now we want to make it, now we want to multiply it by -1. To make it point in the direction of decreasing X. So our vector that's in the right direction, I'm going to call it U vector without the unit vector symbol over the top, now is going to be -1 positive sine of X.
And is that the vector that you drew on the sign?
This U hat,
Yeah.
that is in this direction now. So we're getting there, but it has a length that's not 1.
So the other one, just the one that's tangent to the path at any X value, it's actually going the other way.
The exact opposite way. That's why we multiplied by -1. It was going this way.
Okay. Mhm.
Yep. And so now we're going to normalize this. And so our unit vector is 1 over, -1 squared plus sine squared of X square root times -1 sine X. And so this comes out to be -1 over the square root of 1 plus sine squared X square root, and then sine of X over 1 plus sine squared X square root. So now that is our unit vector in the correct direction. And now finally, our velocity is just this unit vector that gives us the direction times the magnitude of the velocity, which is the speed. And so the velocity as a function of X is the speed times the unit vector. Our speed was 5x squared. So this is -5x squared over that square root. And then 5x squared sine X over that square root. Yes?
So where'd the square root part come from?
Oh, that was just making this, if you have a vector A, B, and you want to figure out a unit vector in that direction, you would go 1 over the magnitude, which is A squared plus B squared square root times this vector. It's what you're doing is dividing that vector by its length. And so you're left with the direction, but a length of 1. And your calculators will do that for you, by the way. Most of your calculators. There's a function called unit V. Yes?
So 1 plus square root of 1 plus sine squared is so close to being cosine.
Yeah, but not close enough. I know.
So what was that last step that you did, the velocity vector times the unit vector?
Yeah. So all of most of the steps were just to find this unit vector that's in the correct direction, that's in the direction of the velocity vector. Now that we have that unit vector, the velocity vector is always just the speed times the unit vector. So that's what I did. We have this function that telling us the speed. And so I just multiplied that to the vector. Okay, so now we have this thing. And now if we want the acceleration, I mean, look at what we're given at the start. Like, there's nothing that looks like we'd be able to calculate an acceleration from this. But now we can see we can, because we have a velocity as a function of position variable. All we have to do is go through the chain rule steps and come up with the acceleration. Also, though, look how hideous that derivative is going to be, you know. And it's hard to make these, it's hard to come up with problems where these are nice and clean, unfortunately. There's one or two simplifications you can make, which means that on tests, I usually what I'll do, instead of making you go all the way through calculating the acceleration, is I'll either give you the velocity as a function of position variable and make you use the chain rule, or I'll just ask you for something like this, calculate the velocity as a function of a position variable. I don't, on homework, I'll make you a couple times go through all the steps, but on tests, I probably won't do that.
So to calculate the acceleration, we'll need to find the derivative.
Yeah, so now to calculate the acceleration, we would just go dv dx times dx dt, and this is the x component of the velocity. So the dv dx is the part that'll give you all the headaches because you have to calculate that crazy derivative. But then you'll just be multiplying it by this. That's your dx dt. So it's a pretty surprising, it's a technique that can let you do some pretty surprising calculations, you know, that would not appear to be solvable. Any other questions about that? Okay. So that is it for the first two of those 4 topics. So next time we'll get into relative motion and circular and spherical motion. Okay, that's it for today. Mm-hmm.